The next topic is the product topology on x times y. If x and y are two topological spaces, then there is a natural topology on their Cartesian product. And to describe that topology, we have this definition. So, say x and y are two topological spaces with their respective topologies tau and tau prime. Then you consider the following collection of sets of the form u times v, where u is an element of tau and v is an element of tau prime. This means that u is an open set in x and v is an open set in y. So, we are considering all products of open sets of x and open sets of y, and we are calling that collection B. It turns out that this collection is a basis for a topology on the product x times y. Note that because u is open in x, u is after all a subset of x, v is open in y means v is a subset of y. So, this u times v is a subset of x times y. This means that this collection is a collection of subsets of x times y, and it turns out that it is a basis for some topology on x times y, and that topology is called the product topology on x times y. Now, simply saying that this is the basis, of course, it needs verification. So, now we are going to verify that it really is a basis for some topology. What is the first condition for a basis? Namely, that whenever you take any point from your set, then there should be a basis element containing that point. What is our set? Our set is the product x times y, where say we have taken any element. Oh, and recall the notation also. Normally we would write x comma y enclosed within round brackets, but the author wrote like this. So, now can you think of an element in this collection that would contain that x times y? Yes, and that element is x times y itself. How is it that this is an element in this collection? That is because in the topology tau, x is also there. Simply because tau is the topology, by definition x is an element of tau. Similarly, y is an element of tau prime. So, this x times y is an element of B, which of course contains this point, and that is how we have the first condition for a basis verified for this collection. And now we go for the second one. For the second condition, we take two elements in the collection B, u1 times v1 and u2 times v2, and of course it is understood that u1 and u2 are coming from the topology tau and v1 and v2 are from tau prime. If you want, you can write those things, but it is understood such that their intersection contains a point a times b. What is it that we have to show here? We have to show that then there is a third element in B which would contain this point and which would itself be contained inside this intersection as a subset. And that third element very conveniently is this itself. We give it a name W so that we can say something about it. Now, we are actually calling this W, but it turns out that this intersection is this product. The intersection of u1 times v1 and u2 times v2 is the product of u1 intersection u2 and v1 intersection v2. It is very easy to prove this set theoretic identity. Okay, it is just simple set theory. And the fact that this is equal to this, that this looks like this, makes it an element of the collection B. Why? Well, what is u1 and what is u2? They are elements coming from tau, the topology on x, capital X, which means they are open sets in x. So, their intersection is also an open set in x. That means this u1 intersection u2 belongs to tau. Similarly, because v1 and v2 are open sets in Y, their intersection is also an open set in Y. That means that is an element of tau prime, and that's why by the definition of this collection, this product is an element in the collection. But that makes everything so easy and in fact trivial, because now we have got a third element W in B, so that A times B belongs to W, because the W is just that, and W is contained in this. Actually they are equal, so of course also contained in this, and that is why the second condition is also true for a basis, and that makes this collection a legitimate basis for some topology on this product, and that's what we are calling the product topology on X times Y. Although the definition of the product topology is itself given by a basis, but we can find other bases also and more convenient ones for the product topology on the product of two topological spaces, and that comes from this theorem 15.1. Say you have a topological space again X comma tau, but this time the topology tau has a basis B. Do not think of this B as that B, okay, this is just some basis of the topology on X itself, and you have another topological space Y comma tau prime, and the topology tau prime also is given by some basis C. Then the following collection, this collection is also a basis for the product topology on X times Y besides the original basis. What is this collection? In this collection we take it is just like that collection B. We take products of this form B times C, where B comes from the basis B and C comes from the basis C. Let's now prove this. In trying to prove that this D is also a basis for the product topology on X times Y, we are going to use lemma 13.2. But for that, we need to first of all make sure that this D is a subset of the product topology. In other words, every element that looks like this, which is an element in D, needs to be an open set in the product topology in X times Y. How do we get that fact? That fact comes from these two containments. Because B is a basis for the topology tau on X, so basically B is a subcollection of tau. The sets that we have in B are themselves open sets, not all open sets but some open sets in X, that means they are elements in tau. Similarly, C is a basis for the topology tau prime, so C is itself contained in tau prime, it's a subcollection of tau prime. And because of these things, it follows that every element in D is open in X times Y in the product topology. Why? Well, the elements in D look like this, B times C. Now B belongs to B, so that means because of this B belongs to tau, C belongs to C, but because of this containment C belongs to tau prime, and that is why B times C actually is a basis element in the product topology on X times Y. You go back to the definition of product topology, that makes it clear that this is not only an open set in X times Y in the product topology, but actually it's a basis element. We however just need it to be open. So this is one condition that we need in order to apply lemma 13.2. That will ultimately give us the fact that this D also is the basis for the product topology. But what is the other condition? The other condition starts like this. Let W be an open set in X times Y, of course, in the product topology, which has a point X times Y in it. What do we have to show here? We have to show here that then there exists an element in the collection D that will have this point inside of it, and that will be contained in this W as a subset. If we can manage to show this, then we are done. Now what do we do? Where do we go from here? We use the definition of the product topology here at this stage. Because it is given that W is open in the product topology and X times Y is a point inside of it, so there will be a basis element of the product topology that will contain X times Y and will itself be contained in W, because that's how open sets behave in a topology given by a basis. So how does a basis element in the product topology look? It looks like U times V, where U is coming from tau, the topology on X, and V is coming from tau prime, the topology on Y. So that's why we write like this. By the definition of the product topology on X times Y, there exists U in tau and V in tau prime such that U times V contains the point X times Y and is itself of, this won't be this, contained as a subset, U times V will be contained as a subset in W. Now next we look at this condition, X times Y is a point in U times V. What does that mean? It means that X belongs to U and Y belongs to V. Now you see the fun part. What is U? U is coming from tau. That means U is an open set in the space X, capital X, and X is a point in U, and the topology tau is given by a basis B. So by the definition of a topology generated by a basis, there should be a basis element in B which will contain that point and which will be contained inside this open set U as a subset. Alright. Similarly, we can write something about Y and V. Similarly, there exists a basis element C in the collection C such that Y belongs to C and C is contained in V. How is this coming? Well, we do not have that thing here. Y belongs to V and V is an open set in the space Y. That means V is an element in the topology tau prime, and tau prime has this collection C as a basis. That is why this is happening. But now we have found a basis element B in this collection and a basis element C in this collection such that B contains X and C contains Y. So X times Y, this point, will be a point in B times C. What else do we know about these collections? About these sets? B is a subset of U and C is a subset of V. So B times C is a subset of U times V, which already is a subset of W. So what have you found here? You have found a set of this form B times C, which is an element of the collection D that contains that point X times Y and which is itself contained as a subset in W. And this is what you wanted. And this and the previous condition together allow you to apply lemma 13.2. So by lemma 13.2, D is the basis for the product topology on X times Y. Next we have this example, example 1. You consider the set of all real numbers and you consider the standard topology on R, which we know is the order topology on R. Now you can think of the Cartesian product of R with itself and you consider the order topology, the standard topology on R as the topology that you are using in both these topological spaces. They are the same and you are going to get a product topology. That product topology is called the standard topology on this product, which we also write as R2. And by definition, this product topology, which we are calling the standard topology on the plane, geometrically this is the plane two-dimensional plane has as basis the collection of all sets of this form U times V, where U and V are both open in R, open with respect to what? With respect to the order topology, which is the standard topology on R. But the result we have proved just now allows us to give this product topology by another much simpler basis, and that simpler basis for this product space is obtained by first considering bases for the topologies that these two spaces have, same topology, so we just need one basis for the topology on R, which is the order topology, and open intervals in R form such a basis. There may be many bases for the order topology, but the open intervals by definition form a basis for the order topology on R, and that is why we can consider products of open intervals, and by the result we proved just now, the collection of all sets of this form will be a basis for the topology on R2. And we also write it properly, including the conditions that here A is less than B and C is less than D. The collection of all such sets, which of course are subsets in R2, will form a basis for the product topology on R2, which we are calling the standard topology on R2. Now recall that in the beginning we actually have seen one topology on R2, namely the topology generated by such sets, interiors of rectangles in the plane. If you remember, geometrically these sets look like that, and actually you can draw a diagram here which is geometric in nature and not just a schematic diagram. That's because you can visualize this as the two-dimensional plane with one copy of R representing your x-axis and the other copy representing the y-axis, and the open interval a comma b on this copy is this line segment. Geometrically, the line segment represents the open interval whose endpoints are not included because it's open. Similarly, this one is represented geometrically by this vertical open interval on that copy of R, again with the endpoints excluded, and that is why these lines are dashed lines, not solid lines. And the region, rectangular region trapped between these lines is what this set is geometrically. I mean, the rectangular region means the boundary is not included, those sides are not included. So the product topology we have got on R2 is not an unfamiliar topology, it is something we have already got. After this, you also have a description of a sub-basis for the product topology on the product of any two topological spaces, which however we will see in the next topology video.